Okay, in this video I'm going to go through this assignment on programming a matrix multiplication based algorithm for the integer distribution problem using Python. Now, the reason I want to use matrix multiplication is that it's a very fast operation in Python, so it's good to try to take advantage. But it may be that we can do even better. At least we can try this and see how well it does. Right? So I remind you about the distribution problem. The distribution problem has a capacity matrix, Cij, and a flow matrix. These are both NS by ND matrices, where NS is the number of sources and ND is the number of outlets or destinations. And both of these matrices we're going to assume have integer entries. So the distribution problem is you have a number of sources and a number of destinations, and you want to meet the demand at each source. The demand at each destination using the supply from each source. And the amount of material that can go from supply I to destination J is Cij. That's the amount, that's the maximum amount can go, and the actual amount is Xij. So the solution to the problem is Xij. Right, so I made a little Excel sheet here to kind of show what's going on. Here I have my supply. Now I have my initial, I specified here initial supply and remaining supply because I'm going to do something with it. But my initial supply is this amount. My initial demand, well, let's see, this adds to 10, so let's make this add to 10 as well. My initial demand is this amount at each of the different destinations. All right. In this case, 3 sources, 3 destinations. And here's the capacity. I can send at most 2 directly from source 1 to destination 1. Here I can send at most 3 from source 3 to destination 2. All right. Now, so far I haven't started assigning supply, so my X here is 0. All right. So this is the basic setup, and I'll use this to refer as we go along. All right. Now, during the algorithm, this vector S and D get updated. So that's these updated values where I say remaining here. So whenever I add more flow, I'm going to update the supply and the demand. All right? So we should consider these as remaining supply and demand, and we call them S and D. So initially, S and D are what are specified in the problem. All right? So I want to define another matrix called the available capacity. And I'm going to use the letter A for that. And that's just C minus X. Okay? So if I'm using some capacity, what's remaining will be the available capacity. Now in Excel, you can see how that will work out. It's going to be equal to this capacity minus the corresponding flow. Right? Now there's a fancy way to do this. Oh, no, actually I can just fill down. And I can fill across also, and that will give me my available capacity. And now, since I don't have any flow here, this capacity is equal to the available capacity. All right? All right. So, now, you can see how these will be related by adding some flows. So suppose, for instance, I add a flow, let's just add a flow 2 here, okay? You can see my available capacity left is 0. Now if I add a flow 2 here, how much remaining supply do I have? Well, here I will have this supply, but I've used up 2 of it, so I'm going to subtract the sum of these 3 entries. Right? Because this is from source 1 to destination 1 to destination 2 to destination 3. Right? So, okay, so that's so, and in fact I can simply fill down to get the other ones. Sorry. Okay. Right. And then if I want to get the demand, the remaining demand is going to be the initial demand minus the sum of these demands in the column. Okay, so it's minus this sum of, minus the sum of flows here. Okay, so this is a complete specification. I could play around with this and get some solution, right? Because here I could just, all I need to do is add more flows. Let's see, I could add another 2 here. Yeah, let's take care of that. Let's see if I can add what I can add here. Let's see if I can add, we can do 1 there. Okay, so in this case I filled 2 of them. And then probably I can, because I do have more capacity, I can probably, I can do 4 here or something like that. Okay. And I have 1 left. Now let's see, can I fill this last one? I guess I still have capacity 1 from here, so I could do that. So here is a solution. All right, so I'm good. Oh no, I'm not, because look, I overdid my bounds. Okay, so this is illegal. I cannot have a negative here. So you know, I'd have to play around with this. Maybe I can do 1 and 1. I'm not sure if I can 1 and 1 here. Okay, is that going to work? No, it's not, because I have a negative here. All right. So anyway, I'm not here to solve this with the Excel sheet. I'm just showing you the relationship between the variables. Okay. So you want to kind of play around and adjust to make things work. All right, now, we always want to use the remaining supply to meet the remaining demand. Well, let's get back to a feasible, let's get back to something feasible. Let's take this one out. We'll call that 0. Okay. All right. So I do have remaining supply here. I want to use this remaining supply to meet this remaining demand. All right. In this case, actually, it looks pretty easy. I could just put a 1 here. But anyway, sometimes that's not possible. Okay. Now, in this case, in this simple implementation, we're just going to meet remaining supply 1 unit at a time. So there will be several iterations. We'll just add units 1 by 1 and make sure that when we add the unit, we don't get negative numbers. Okay. And since computers are fast, I can add millions of units just in a second. And as I said, to find the alternate flows, we can use matrix multiplication, which is computationally very fast. Right, so here's the algorithm description. Right? Now, while D is not identically the 0 vector, this is a while loop here. If you're not familiar with that, you can look that up in Python. So this is going to be, when I say remaining demand, this is this remaining demand, and this is what I'm calling D. And then this is remaining supply, and this is what I'm calling S. Okay. And capacity is what I'm calling C. Okay. Right. Well, I didn't want that. Stupid thing. Okay. I have to fool it so that it doesn't do that. Okay. All right. So these correspond to the variables I have defined here. All right. Now, if you remember in the book, to do the rerouting may take several stages. And I'm going to record those stages in a list. And then once you find the result, you have to trace back. All right? So I'm going to create a list of column vectors, W lists. These lists will contain suppliers with supply that can possibly be rerouted. Okay? The first entry of W list is the remaining supply S. So I have a list of vectors. A list of vectors. Okay, so the first element in that list is S. So I don't know if I haven't actually tried this, but let's see if we can do this. I'll put W list here. Okay. And my initial W list is going to be the remaining supply. So let's go back and we'll zero this out and we'll start at the beginning. Okay, so just and let's just make everything zero. Whoops, sorry. Okay, there we go. Okay. All right, so W list, the first W list would be this value here. And it's going to be difficult to do this, but we'll see what we can do. Oh, sorry. So that's the first value. Okay, so that can possibly be rerouted. Okay. Now I want to compute this matrix here. Where A is so this is actually a matrix multiplication. When I take this sign here, NP means numpy, so this is a numpy operation. When I take sign here, the result is going to be either zeros or ones, because this can never be negative. Right? So I'm taking the sign of this matrix multiplication times what I call mask matrix, where mask matrix is a matrix of the appropriate size, which is 1 everywhere except on the diagonal, which is 0. Okay. So let's see if I can show this. Mask matrix would be It's 1 everywhere except it's 0 on the diagonal. So what I'm going to do is I'm just going to put 1s everywhere. Sorry, I made a mistake there. And then we'll do here. Right. So mask matrix would have 0s on the diagonal. Okay. Right. Now, it's a little bit difficult to do matrix multiplication in Excel. There is a way to do it, but I don't particularly want to look it up now. But what I'm going to do is want to take the sign of A times X transpose times the mask of MX. All right. So what does this actually do? Just what I've noticed down here is that this star here means element-wise multiply, and the @ sign means matrix multiply, and those are two different things. Okay. So M is considered as a rerouting matrix. If Mij is greater than 0, then there's available capacity from source I that can replace supply from source J. Okay. So what's going on here? What is A times X transpose? Maybe I can write that down here. Unfortunately, my tablet is not working well. I think I got a Windows update, so let me see if I can do something here. It's just going to let me do something. Okay, there we go. Okay. So if I want to take A times X transpose, you can write this in summation notation. That's going to be equal to the sum, and then here I'm going to have, I'll call it J equals 1. Now the sum is over what limits? So let me undo that for a second. The sum is from J equals 1, and what's the top limit? Well, the top limit, because when you do a matrix multiplication, you multiply the columns of A by the rows of S. Now, the number of columns of A is the number of destinations. So that's ND. Okay. Okay. And this is going to be the IJ entry of A times the JK entry of X transpose. But the JK entry of X transpose is the KJ entry of X. Okay. So if I want the IJ entry of this matrix, I want the IJ entry of this matrix, that's in row I, column J. It's going to be the sum over AIJ times XKJ. All right. Now, think about how many rows and columns this has. A has the number of source rows, number of destination columns. X has number of destination rows and number of source columns. So in fact, this is a NS by NS matrix. Okay. Okay. That's what the size is. Okay. All right. Now, what's the significance? Well, the entry is going to be non-zero if and only if there's a J that has AIJ and XKJ non-zero. Okay. So this entry X transpose IJ is non-zero. Sorry. Is non-zero. Why is it doing that? Is non-zero if there is an I and K such that there's available capacity from I, and there's currently material shipped from K to the same source. Okay, both the material from I is going to J. The capacity from I is going to J. The material from K is going to J. Okay, let me replace that such that there is capacity from source and shipment, I hate this because it always does this. I'll have to do it this way. Source I, and it's screwed up again. All right, sorry. I. And material, there's, say, additional capacity and flow from source J to the same destination. Okay. Now, what does the mask do? If I just do it this way, it's possible that this should be AIK. AIK. Okay. All right. So this means, what does this mean? This means that if there is additional source, if there's additional material at source I can send the material from source I instead of the material from source, this should be source K, sorry, not source J. Material from source K, okay? They go to the same destination J, all right? So let's make sure we have this right. Let's make completely sure we have this right. Okay, we have this here. They have the common J. Both I and K are sources. J is a destination. This one says there's capacity from source I to destination J. This one says there's flow from source K to destination J. All right. So there's additional capacity from I that could replace the flow from K. So this is why I call it a rerouting matrix. Now this doesn't take into account the fact whether or not there's additional material at source I. But if there is material at source I, then I can reroute it and replace the material that comes to destination J from source K without reducing the supply to source K. Okay. So this is said that if there is additional material at source I, okay, it can substitute for the material being shipped from source J. Okay. So that's going to be a key thing because if we have a shortfall to some particular destination, we're going to want to reroute. And this is telling us that, for instance, if I could reach this shortfall destination with material from K, I could reroute from I and free up another unit from K to meet that unmet demand. Okay, so that's the rerouting matrix. Now the reason why I'm actually not 100% sure that I need to put that condition with the mask matrix. So like I said, you don't want the I and the K to be the same node, because then you're just taking it from a node and putting it back into itself. So you want to make sure that these are going to be different. Okay. All right. Now here I said Mij. Let me say Mik because that's the notation I use below. Okay. All right. So this is indication of what can be replaced. All right. Now, if you look in the book, sometimes this replacement may take several steps because you might have to replace in several stages in order to make up the shortfall. And that's why we want to have this W list. W list at the beginning is telling me how much available that I have immediately available to reroute. But it may be that after I reroute some of this, I'll be able to reroute twice and my W list will change. So we're going to have successive remaining supply vectors, and you'll see how that works. All right. All right, now, so we're going to loop. I'm loop over the range of ND. Why? Because the number of stages in rerouting can't possibly take more than the number of columns. Okay, because each time you reroute, you'll get at least one more accessible destination. If you don't, then you've stopped. Okay. All right. So first of all, So here's my available supply. So I let W be this, okay? And if I have this, then that means I break. That means I've actually found a way to meet some unmet demand. What does this mean? This W transpose times A times D transpose. What that means is that I have, so the meaning here, sorry, meaning, the meaning here is that I have the fact that this is greater than 0, there exists a K, well, I'll use I guess I can say I, J, and K, okay, such that W I times A I J times D J. Actually, I don't need a third index here. I and J. Is greater than 0. Right? Because every element in this product, in fact, this product is a number. And this number is the sum of products like this. And the only way this product can be positive is if you have an entry that's positive. And this means that there's stuff at source I, an available capacity to send it to source J, and unmet demand at source J, right? So I already have identified some path to meet some unmet demand. Okay. So I can say, so sum of the unmet demand at node J can be met from source I. Okay. Right. So if this condition holds, I'm going to break. Okay. Now, as you saw in the book, that doesn't always happen. It's going to happen a lot at the beginning, because you're going to have, like if you look here, there's an awful lot of available capacity to meet the different demands. So at the beginning, this will fill up rather quickly, and you'll have this option being taken most of the time. It's just towards the end that this is going to happen. Okay, all right. Now, all right. So, So if this fails, then we're going to have to do some rerouting. So here are the rerouting steps. Okay. All right. So what I want to do is find out when I reroute, I'm going to get secondary sources. For example, if I reroute and I can replace a unit from 2 with a unit from 3, then that frees up 2. That means I have an additional supply node. Essentially, I can supply from 2 because I can reroute from 3 to supply to make up this shortfall from 2. All right. So that means that 2 becomes an additional sort of virtual supply mode. Essentially, it's a supply mode, even though it doesn't. Even though this value of remaining might be 0, I can reroute. So it's a reroutable supply node. Okay. All right. All right. So what you do now is you simply, since if it doesn't work directly, you do the rerouting. Okay. So I do a rerouting, and that shows me the new the new essentially nodes that are essentially supply nodes, and then I'm going to add this to my list W list. Okay. So my initial W list was S, and then I just keep on adding more and more vectors to the W list, because I'm going to have more and more sources that are accessible after multiple stages. Okay. And I keep on doing this until I find a path from my secondary or my substitutionary supply node to my unmet demand. Okay, and then what I have to do is trace back, because I have a sequence of these vectors. I need to figure out how I actually do the rerouting. And I'm not 100% sure I did this right, and we'll find out if I did do it right. But let me run through this, and we can work this out together. All right. All right. Now, if this product is greater than 0, I should be able to go back and find a I and a j such that this particular product is 0, and that means that this source to reroute can meet this unmet demand. Okay. If I can meet the unmet demand, I can subtract 1 from the demand at j. Right? And I'm going to have to add 1 to the. I'm going to have to supply that from I, because I've determined that after rerouting, I can get an additional unit from I. Okay. Now, if I add 1 to xi, that's adding 1 to the flow, I'll have to subtract 1 from the available capacity. All right. Now, where is this 1 coming from? So we'll have to look back and see how to do the resupply. And you can see that this matrix is coming in again. All right. So what I have to do is I have to resupply this. I have to substitute some flow from this ith node. Okay. And so I'm going to compute this rerouting matrix again. And this shows me sources that could potentially free up a unit from source I. Okay, so I'm going to reroute. Source I is supplying a node, and I'm going to substitute that supply with supply from another source. Okay, all right. So now the available supply is in W list n. Okay, the available supply at the end stage is in W list n. Okay. So I want to see what of those available supplies can substitute for I. So I need to multiply this by the ith column of m. And that will tell me what can substitute for I. Okay. Now I don't need to substitute with many sources. I only need one source. So I'll take the index of this entry to be k. Okay. So this identifies the supplier whose supply can be rerouted to free up a unit from source I. Okay. And then it remains to find the destination to reroute to. How am I going to free up that unit from source I? Well, I'm going to have to reroute something that I is sending somewhere else and send it now to the final destination. Okay. All right. So I'm going to compute the element-wise product of the kth row of A times the ith row of X. Okay. Now, what is the kth row of A? This is the available capacity from source K. What's the ith row of X? This is what's actually being sent from source I. Now I want this available capacity from source K to replace the current flow from source I. So I need to find some entry where both of these vectors are non-zero. So when I compute the element-wise product, that will only be non-zero if both are non-zero. Okay. All right. So I can say let J be the index of a non-zero entry of T. So, okay. So this J identifies a destination which is receiving stuff from I and has additional capacity to receive stuff from K. Okay. All right. Okay. I don't know why I completed that way. Okay. So that's why. What I'm going to do is I'm going to take one unit that I is sending to J and replace it with one unit from K sending to J. Okay. All right. So what I need to do here is actually this is not right. This should be KG. I think this should be KJ. Okay. Yeah, because I'm taking more from J. I'm adding one unit to XJ. I'm adding one additional flow from K. Okay, so doing the rerouting from source K. Okay. All right. So that's fine. Okay. Hang on a second. Let me think about something. Okay, well, I see now I need to add another step here because, in fact, since I do the rerouting from source K, I also need to reduce the flow from node I to node J. So I'm going to have to do, instead of this one, I'm going to have to do, okay, it's not cooperating. Okay, there we go. Okay, all right, so here I'm going to subtract one from, okay, instead of supplying from I, I'm supplying from K. Okay, and then here I need to add one to Aij, okay, right? Because I'm no longer sending that unit from I. In fact, I'm sending the unit from I somewhere else, and that, in fact, I sent the one up here. Okay, I've already done the subtraction here. Okay, so here it says, so this is going to be remove the flow to J from K. That is substituted. Okay. All right. Now. So what I've reached at the point here is that really I'm back in the same state I'm at before. Now I have a node J that I need to supply from node K. But I'm not sure that node K has the material that I need. So I'm going to have to make sure that that can be resupplied from a node farther down the line. So I'm going to go back and do this same thing. Remember up here, I was the source that was supplying the additional unit. So now here what I called K here is now taking the place of I. Okay? So I have to repeat this loop, this time with the new I and the new J. So if you see here, the fact that these here are inside of this bullet point means that this is where the loop ends. Okay, so I'll just note that. So here is where the loop starting at 4 ends. All right. So this whole step 4, the reason why this is indented is just like in Python. If you have indented code, that means it's inside a loop. So I'm showing the same thing. All right. Now, once you've reached the end, presumably you should have reached a place where you have a source with available material. And that's how we designed it, because when we went forward, we started with sources that had material. So I'm now going to pull that additional unit from source I. So since I pull that unit from source I have to decrease this. I'm actually not sure I need to do this. Let me think about this for a second as well. All right, I'm thinking here that you don't need to do this because we've already done the decrease. So I'm going to remove that. Okay, so there may be some technical points here that we need to clean up. Okay, all right, because, yeah, I think we've already removed it here. So we may have to trace through and see what's going on here. Okay, all right, so after we've done this, then this is where that loop finishes. Then this one here, at this point, we have changed the flow, and our change is finished. We've added one more unit to meet unmet demand, and we've subtracted one unit from available supply, and then you go all the way back to point 1. Okay, right? All right, and so once you do that, now the way this will terminate, eventually it will terminate here. Okay, because at some point, it will terminate here. because once D is the zero, identically the zero vector, then you just have finished. Okay. Okay. So either there's no feasible solution, or X is the solution, is the flow, is the required flow. Okay, all right, so the first thing, of course, you want to do is, so you need to please implement this in Python. Now, if that's really difficult, come and let me know, and we can do some alternatives. And you can use your choice. If you want to use Colab, that's fine. Or if you want to use Jupyter Notebooks and Anaconda. Or Spider. And I know some people use PyCharm or something like that. You can use that also. It may be harder for me to. Well, I suppose if you send me the Python file to debug, I can still debug it. It's fine. Okay. I'm not sure what this is doing here. I'm going to remove it. Okay. All right. So 2. Try to make the algorithm more efficient. Okay. Oh yes. Okay. And then you can say, I should say, test it on. Let's do some examples from the book. Let's say 3 examples. Okay, and see if it works. Now, eventually we'll try some larger flows. That will be interesting. We just want to make sure it's working first. Okay, now, I don't think this algorithm is as efficient as it can be. Because, for example, here we're just increasing the flow by 1 each time. So maybe you can modify it to increase by more each iteration. Okay, because, say, in the book he did that. But that was kind of heuristic. It wasn't a systematic algorithm. Okay. Now, if you look back over the computations in this, what's taking the most time is this matrix multiplication here. So can that be reduced? Right? A matrix multiplication, so for instance, this one is a NS by ND, and this one's a NS by ND, ND by NS matrix. So that's going to be actually ND times NS squared operations, which is not so much if you have, 10 by 10 matrices. But if you're getting up to 1,000 by 1,000, that's going to take a lot of time. So how much of this do we really need to do? For instance, I computed M here, and I basically computed the same thing down here. Do I really need to compute it twice? And here also, here I'm computing this matrix multiplication. Do I really need to recompute these matrix multiplications each time? Can I update in a intelligent way? Also, do I really can I just store some variable and not do the recompute? For example, just to show you here that during this loop, A and D don't change, so I really don't have to recompute A times D transpose each time. I could just store that in a value. Now the W does get updated, but this one does not. Okay. So, and another thing is it really the best way to use matrix multiplication? What we're really trying to do is find non-zero entries of this. There might be a better way to do it. Now, do not use loops. Avoid using loops as much as possible. So let me just say that. And I'll say, do not use more loops. Loops are no. They're okay in C, they're okay in Fortran, but they are definitely off limits in Python. I have loops here only because I have to. Any other loop is not necessary, and it's going to greatly increase your computation time. So do not use more loops. Right? Use vector operations. That's really the way of the future, because loops are not parallelizable. So if you know something about parallel computation is the way of the future. So avoid using loops as much as possible. Okay. So like I said, instead of increasing by 1, try to get the maximum increase. Is it really necessary to recompute M? Okay. So there's some. So and then you can say other ways to make the code more efficient. Okay. There may be a completely different approach. You implement this way, see if you can do it, see if you can get a better result from some other code structure. All right, and we'll have to make sure that this code actually works. All right, well, have fun with this, and if you have trouble, please get in touch.